Hello everyone. In the last lecture we have discussed about shock wave produced under impact. So we discussed about planar, parallel and normal impact. We derived expressions for pressure generated during this impact. So in today's class we will continue that. So we will solve some numerical examples, that is basically from the Mark Mayer's dynamic behavior of materials book, and we'll solve a couple of problems, and then we will speak a little bit more about this shock wave. So the first problem is, let's say, right example, numerical example is one. Let's so this is let's assume that we have a projectile. I'll draw a projectile like what we did in the last lecture. So we'll draw it like this. So this is a projectile and this is the target, and the projectile has a velocity, impact velocity, which is, let's assume that 800 meter per second, which is kind of close to the speed of AK-47 bullet. So now let us assume that so we have the same material in both the projectile and this is, let's say, the steel, and for example we have SS304, this is a special kind of steel. So so this is the steel we are using for both projectile and target. So here in this problem we need to calculate the pressure P generated by this impact. So this is our goal, calculate the pressure P, and we need the properties. So we need the shock parameters needed for equation of state, and those parameters are shock parameters C naught and S. So C naught is 4.57 millimeter per microsecond and S is 1.49. So 4.57 and also we need density, this rho, which is for steel 7.9 gram per centimeter cube. So we can convert this 7.9 per gram per centimeter cube into kg per meter cube. That will be 7900 kg per meter cube. So we will keep it into all in SI units, and here for 4.57 millimeter, that means again 4570 meter per second. So we need to calculate the pressure, and before that we need to have the particle velocity. In the last lecture we derived that the particle velocity for an impact which has both the projectile and the target as same material. That means if we have steel in both the materials, then the particle velocity will be UP will be equal to half of V, the impact velocity. So this is particle velocity. Particle velocity, whatever particle velocity will be generated after the impact, or so this UP equal to half V. So which will be equal to 800 by 2, it is 400 meter per second. And then from earlier equation where we had that pressure generated in the target and the projectile will be same, and P1 equal to P2, which will be equal to rho naught 2, where 1 is for projectile and 2 is for target. So, rho naught 2, sorry, that is the density of the target multiplied by the parameters for the equation of state, thus as to u P2, this is all for the target, and multiplied by u P2. So, in this case we can take the density as we know 7900 multiplied by C2, which is nothing but the C naught what we wrote it here, that will be 4570 plus S will be 1.49 without any dimension, and then UP2, which we have found at 400 meter per second here, 400, and then the whole thing multiplied by 400. So, this will give us it's a big number. So, there will be 16.3 10 to the power 9 Pascal. So, all the units, if you see that this is in all are in SI units, this is kg per meter cube, and here also this is these are meter per second, meter per second, meter per second. So, this will be the final result will be 16.3 10 to the 9 Pascal. So, which is nothing but we can write as gigapascal, 16.3 gigapascal. It is a very high pressure, 16.3. So, pressure is 16.3, pressure generated due to the impact. So, that is what we wanted to calculate. So, this is our final answer. So, we will discuss about one more problem now. This problem is from Mark Mayer's, that our textbook what we are following, Mark Mayer's book, but again originally this solution, the analytical solution is from another literature, that is Kinslow 1970. So, in this case we will take two different materials for projectile and target. So, this is a projectile and this is the target. So, our projectile is tungsten carbide, our projectile is tungsten carbide, or you can write WC is the symbol we use for tungsten carbide. And so, here this target is steel. Let us assume that the velocity will be 1200, this is meter per second, and that is the speed at which the projectile will impact on the target. So, what we need to calculate? So, we need to calculate the pressure again in the target and the projectile, pressure generated in the target and projectile. So, for that we need the equation of state for these two materials, equation of state for these two materials, and also we need the density of these two materials. The density of steel, this rho, I will write rho naught T, T for target, and this will be, we will at 7.85 gram per meter square centimeter cube. Let us assume this is a little bit different than the earlier one, because that was SS 304, with 7.9 and this is 7.85, and here tungsten kyber is very heavy material, it has very high density, that is 15 gram per centimeter cube. Now, for equation of state for these two materials are for, let us say, for tungsten carbide, the equation of state is US, the velocity of the shock wave is equal to, okay, I will write it, it should look like C naught plus S1 or SUP. So, now in this case this is for tungsten carbide, or better I will write this is a common equation, and then we will say the tungsten carbide what is the equation, and for steel what is the equation. So, for tungsten carbide this equation is looks like 4.9 to 1.34 UP. So, UP is not known now, the particle velocity, and then again for steel the equation of state is 3.57 1.92 UP minus 0.06 8 UP square. So, you were concerned about these last term. So, as you know, actually for the equation of state is this is only the linear relationship, but we can extend, you may have the more terms here. Here if you write S1, S2, that can be UP square, or there can be even higher terms that we already discussed about that. So, for steel due to some complex behavior, not maybe all steel, but for some material then that may be arising due to some complicated behavior like phase transformation or so. So, we have one more term which is a quadratic term UP square. Unit of these 3.57 or 4.92, we should understand that this is in millimeter per microsecond. This is again millimeter per microsecond, and this is S1 and S2 dimensionless. So, what we will do now is from our earlier derivations, earlier relations we discussed in the previous class. So, we need to set that the P1 is equal to P2, and that will give us something that the expression for UP, and that will be like little complex expression is B square minus 4 AC, the root of the quadratic the equation divided by twice A. So, we will write what is ABC here, but again I want to tell you. So, for in this case we will ignore this quadratic term. So, we will not consider this quadratic term because that will make our calculations simple. So, this in this UP that is what we discussed in the last class. So, what is A, B and C? A, B and C, that is rho naught T, T for target. I will write T for target in the subscript, and P for projectile, or we can even use number 1 and number 2 as well, 1 or 2, whatever we discussed in the earlier derivation. We keep it as 1 and 2, but today we will keep it as T and P. So, this is rho naught T ST minus rho naught P, P for projectile, and then SP, then B is rho naught T CT for target, rho naught OP for projectile, CP, and then twice rho naught P, that is the density of the projectile material, and SP for projectile, and V, the impact velocity. And then C will be equal to minus rho naught P for projectile, C this shock parameter for the projectile material, multiplied by V, the impact velocity, then rho P V square. Sorry, this will be S1 SPV square. This will be SVV square. So this is the expression, and then we know that rho naught T, as you can see, 7.85 gram per centimeter cube, or we can write it as 7850 kg per meter cube. Here actually we did not write the subscript, but this is rho naught P, and that will be equal to 15,000 kg per meter cube. And then we have this C naught, CT or CP, these are nothing but this, so this is CT for the target, and this is C for projectile. Similarly, this is S target, and this is S projectile. So now using this, what we can get is the expression. We are not going to calculate in each and every step, so I will write the final expression. This will be 150.03 plus minus 141.96. So divided by minus 10.026. So we have a plus minus sign here. So we will get two roots out of here, and then these two roots are, fortunately the both are, we have positive roots. Actually this is, we can write it in kilometer per second, or this is nothing but actually 805 meter per second, which is 80 per meter per second. So actually what we can do is that in these calculations you need to be careful now. So because we can have these densities in kg per meter cube, then we can have these C naught values, which is let us say CT will have 3.57 into 10 to the power 3 meter per second. It was, if it is millimeter per, here it is millimeter per microsecond, and that way if you convert everything into meter per second or kg, so what will happen is this, I think we can directly write it here even. So UP, the one root is UP 8 meter per sec, 805 meter per second, and the another one is 29020 meter per second. So but this is a very high value. We can see that this UP is 29 kilometer per second. It's quite high, and anyways both the roots are positive. We can take only the positive roots, not negative. And here we can see that there is a very high value, which is even higher than this. UP is higher than our impact velocity V. So our particle velocity cannot exceed the impact velocity UP, so that is why we will neglect this one, and we will only go with UP equal to 805. So that means our impact particle velocity in this impact will be 805 meter per second. That is the particle velocity because of the impact. So, now we will we will do the calculations. Let us say the pressure generated in the target, that will be rho naught T, Ct, all these subscript T for target, St, Upt, Upt. So, this will give us 32.3 10 to the power 9 Newton per meter square. We can write 32.3 gigapascal, and then pressure generated in the projectile, or we can write it here, target and projectile. So, these are both pressure. So, rho naught P for projectile, Cp V minus Upt, this will be for target Upt, not for projectile. So, if you remember our earlier derivation, so this Spv minus Upt square, this is also T, not P. So, from this we will get the value as 32.5 multiplied by 10 to the power 9 Newton per meter square. That is 32.5 gigapascal. So, we have the pressures are they equal, actually they are almost equal. Our condition was the pressures are equal. So, anyways, we got this pressures generated in the target and projectile, which has a very high value 32 gigapascal, 32.5. But there is another way to the solution. So, what we did is the analytical solution. We will go back and we will write here. So, this was the analytical solution. So, we will go for one more solution, which is graphical solution. This you may find it to a faster solution. So, graphical solution is this is actually also called a impedance matching technique. So, basically we need to plot this here on the x axis the particle velocity and the y axis the pressure. Let us say pressure we are writing in gigapascal, and particle velocity, as we know, this will be meter per second. So, now if we draw this, so these two equations what we derived earlier in earlier classes. So, P2, that is for target, rho naught to C2 plus S2 UP2 UP2, and then for pressure P1 is rho naught 1 C1 V minus UP2 plus rho naught 1 S1 V minus UP2 whole square. So, this is for projectile. I do not want to confuse you again. So, probably we can write all this as T. So, these all 2 will be replaced by T. Sorry about that. So, just to make you not much confused. So, these all 1 we can replace by P for projectile. This is P, and this will be P. So, PP means oh sorry, this is T, this one is T for target. So, only these two are target, but otherwise this expression will have all P subscript. So, now so these two equations that we derived in the earlier classes, we will plot it here. So, this will look like, I will do very rough sketching here, then you can check this all these diagrams in the book. So, it is directly from the book. So, this will look something like this, and that is for the target. So, how the pressure will vary with respect to the particle velocity, and similarly for the, that means what we are doing is we are plotting these equations for the target equation, and then we will do the other one. So, this one will look like something like this, and then this is actually for the projectile, and as you know, this projectile, this one should be your impact velocity, that is 1200 meter per second. So, that is 1200 meter per second, because the projectile we are plotting UP, that UP cannot be higher than the impact velocity. It will start from this, and then the particles in the projectile. So, if you draw this is the projectile P, it is coming at a velocity v, and it is hitting the target T. So, the particle velocity in the projectile before hitting will be 1200 meter per second. If you are if you have an observer outside, and this is the observer. Now, after hitting it will change, and then we can have this plot P versus UP like that. And similarly for target, the initial velocity was 0, the particle velocity is 0, and it will increase, and it will go to other extent. So, this is these two equations we plotted, and that is that means for projectile when UP will increase, this pressure will decrease, and for the target with UP the pressure will increase. So, now the solution of this is the intersection of this curve. So, this P, that means this is almost what we got is, if we plot it accurately. So, what we will get is it will be close to 32 gigapascal. So, this point will be the solution is P will be equal to 32, around 32 gigapascal, or what we got in the earlier analytical solution. So, what we did it here is we plotted these two equations. We know the relation between the pressure and the particle velocity, because we have the other parameters with us, and density and the parameter C and S, and that is for the target. So, what we did is we have we start from the this point, and we got this for this curve for target, and similarly we have another curve which starts from that V equal to 1200 meter per second, that is the highest maximum particle velocity, and that curve looks like this. And if these two curves when it will meet, that means as we have already in the earlier derivation, we set the condition that the pressure should be equal, and our even the particle velocity should be equal. So, these two, from these two conditions, what we can get is P is 32 gigapascal. Our UP, whatever we found UP will be around 800 meter per second. So, that was we got like 805 meter per second. So, this is because our conditions were earlier that the pressure and the particle velocity will be same in the projectile and target. So, this is the graphical solution or impedance matching technique. So, this is as you can see that this is a faster technique than the analytical one. So, also if we get these parameters like P or UP or UP1 or UP2, that means for target or projectile, this is basically we will say that pressure and particle velocity, pressure and particle velocity. If we know these two parameters, we can obtain the other shock wave parameters and using a Rankine-Hugenoid equation. So, if we get the pressure and particle velocity, then what we can do is from here other shock wave parameters can be, or shock parameters we can. What are the other parameters? As we know that we got total 5 parameters, and the other parameters are will be shock wave velocity US or the internal energy like E. So, these we can find it out. So, we know the shock parameters are that earlier we discussed that there are 5 parameters: US shock wave velocity, UP particle velocity, then we have the pressure, and then internal energy, and then density, or we can write it in terms of V as well on the volume. So, so we have these 5 parameters, and then if we know 2 of these parameters, only 2 are required to determine, find the remaining ones, remaining parameters. Provided this we have these provided we have UOS parameters known. UOS parameters means C and S, if they are known, and then only we need to know only 2 of these parameters, so that we can find the others. And so, we have 5 parameters. We can have from 5 parameters we can have 10 pairs of these 5 parameters, pairs, or we can say that 10 relations that can be we can have in the both way, then that can be even 20 equations. That means suppose we have a relationship between V1 and US, let us say V1 and US. So, that can be written as this relationship is written as V naught 1 minus 1 by S plus C naught S US, and otherwise if you write the relation like US and V naught, there will be like US is equal to V naught minus S V naught minus V1, and on the numerator it will be C naught V naught. So, just to show you that this is now one pair, this is the pair which we talked about, these pairs. So, and then there can be 2 equations from these pairs, and you can reverse it, and that is how you can get 20 equations out of these 5 parameters. Then we will talk about this shock wave profiles. We will show some plots. Shock wave profiles. So, first we will see a real idealized shock wave. So, there is one idealized shock wave which the plot will be different than the real ones. Look something like this. This one is idealized idealized shock wave profile. So, this has time in and x direction, and then stress sigma, or displacement we will write small u for that in this y direction. So, this will look like something like this. So, stress will increase with time, sharp increase. That is actually a discontinuity. This is discontinuity. It's going to like a sharp increase. This is we call shock front. Here that's actually pulse duration, and this is we call the release. Here you can see that first part, you can see a discontinuity as a vertical, it is going vertically up, and we have a plateau here at the top, that will continue for the pulse duration, and then release, that will be the gradually decrease, gradual reduction of the stresses. However, in the real case, it's a general realistic shock wave profile. So, what will happen here is with time we will show this actually a velocity profile. This one is a velocity profile. We will discuss about this VISAR. This is called this is VISAR technique. We can discuss about that later in later chapters. So, this is actually nothing but velocity interferometer system for any reflector. So, that is a technique to know the velocity profile. So, here what will happen is first there will be a steep rise of pressure or particle velocity. So, it will be steep rise, and then there will be we will have some slope in that part. It will go again steep up, and this will look like this, and then the plateau comes something like this. It will go down and go up, something like that. So, this is elastic part, elastic, it is elastic modulus, or then this limit is called HEL, which we will discuss again in later. So, this is Huguenot elastic limit. So, after this limit, this pressure or the velocity, let us say particle velocity, will have a increase like this, and this portion will depend on the constitutive relations, constitutive relation of the material, constitutive behavior of the material, this part. And then this is actually the plastic part. This will give us the plastic modulus. Here will this will be the elastic modulus in this part, in this range. And then this can happen due to phase transformations, as we will discuss later, that due to high energy of the shock, the material can change the phases. I mean, phase transformation can happen, and then this the pulse duration play too will get, and that is it's called as Hignoid state. And then the unloading curves, that is it is actually elasticity first, and then first elasticity it is written as Hignoid pressure elasticity, and then first it will be elasticity, and then it will show plasticity in the later portion. And this this is actually related to spalling, that we will discuss in the next lectures. The spalling is nothing but the wave when it reflects back from the free surface, and that can actually generate fractures. So this will be called as this is called as falling, and we will be discussing that later. And so this is basically, this curve is from the reference Grady 1991, although we have taken it from the Mark Mayer's book, but this is actually the originally from the Grady's 1991. And just to let you know that what is visor, I already told you that what is this velocity interferometer system for any reflector, and this based on laser interferometry. So this based on laser interferometry. So that means this is the based on interference of interference fringes that appear when different laser beam interacts. So that we can discuss later about these this one. And so at last in this lecture we will talk about this shock response in a for 3 different cases. So this will be, this curve is a sigma x variation with 1 minus b by v naught. So this is a little bit different than what we got the Hignoid curve earlier, but because this is, if you see the x axis we have v by v naught. The earlier we plotted p pressure with specific volume. So but this curve, the Hignoid curve, will take a shape like this, and however the pressure volume curve of a material is not exactly the like a Hignoid curve, because it looks something like this. It looks something like this, and this is because the Hignoid curve has only hydrostatic component part, and this may have both the hydrostatic and deviatoric, because in Hignoid we have ignored the deviatoric stresses. So and so this is the Hignoid elastic limit HEL, this point. So, this rate of increase of stress is much higher in this rate of increase of stress is much higher in elastic region, that you can see from here. And then there can be three cases here. The first case is flow strength of a material is independent of pressure, P. So, this is, let us say, this curve. And then second case is the flow strength of material decreases with pressure, with P. So, this curve can be look like this. So, if this is the number 1 and this is number 2, and the number 3 is the flow strength of material increases with pressure. So, this can be something like this. So, number 3, those are these 3 different the cases, we can draw it like this. But basically the Hignoid curve is different, because we do not have the derivative component of the stress, we considered only hydrostatic part. So, that is why it has a difference with the other curves of different materials. So, yeah, that is all for today. So, what we discussed here, if you try to remember, in the previous lecture also we discussed about the impact of projectile with a target. That is a planar impact, planar, parallel and normal impact. So, in today's lectures we discussed a couple of numerical examples, and to how to determine the pressure, and even we discussed about a graphical method which is called impedance matching technique, and also we saw some shock wave profiles and shock response of some materials. So, in the next lectures we will discuss about equation of state for shock waves, and also we will have some discussions on the shock wave interactions or reflections. So, that is all for today. Thank you.